Hello and welcome to another video. In this video we're going to be working on element appearing more than 25% of the time in a sorted array. And in this problem you're given a sorted array in non-decreasing order, and there's one integer that occurs more than 25% of the time. Return that integer. So for the first one it is 6, and we want to return it, and then the second one there's 1. So essentially, obviously there's like a super easy way to do it that I will briefly discuss, and then we can talk about the cool way to do it. So the super easy way, we just take some length, right? Like let's say we have a length over our array here. Let's 2, 4, 6, 8, 9. So we have a length 9. We divide by 2, or not by 2, by 4, and then we realize that our length here is 2.25. So we need an element that occurs more than this. And because our array is sorted, we can just traverse that array and maintain a count of our current element. So we'll say like, okay, we found 1 once, we found 2 twice, we found 6 4 times. And as soon as we find an element that occurs more than 2.25 times, we return it. So it's really straightforward. Just loop through it, keep track of the current element. As soon as that is more than that, you just return the element. Super easy. So that's not the one we're going to code up, though. We're going to code a more interesting one. So let's look at this array one more time. So we have 2, 4, 6, 8, 9 elements. So let's actually make an array of 9 elements. And then we're going to kind of see an observation that we can make. So this is 2, 4, 6, 8, 10. So let's get rid of this one. There we go. And let's also index these. So let's also make it bigger. So there we go. And index them. So we have like 0, 1, 2, 3, 4, 5, 6, 7, 8. And remember before, our complexity would have been of n, right? Because we're essentially traversing through an array. Worst case scenario, our number is all the way at the end, and we have of n. Okay. So same kind of thing for this problem. So let's say our length is 9. So we need an occurrence. Instead of figuring out like what number do we need, like before we need it to occur more than 2.25 times. Instead of that, let's actually just get an actual number, right? Like, because like we don't want to know 2.25 times. We want to know exactly how many times it needs to occur for it to be a success. How do we do that? Well, we just divide our number by 4, right? So if it perfectly divides into 4 like this, then we would need it to occur 3 times. And if it has a remainder, we'd still need it to occur. So if it's like 9 by 4, what we can do is we can just, instead of dividing like this, we can just floor divide our number. Now we'll get 2 for this, and we'll also get 2 for this. And for both of these, we want it to appear 3 times. So we take our length, floor divide by 4, and add 1 is how many times we need it to occur. So in this case, we need it to occur 3 times, right? Okay. Well, if we need it to occur 3 times, that means that there has to be some chunk of elements, some chunk of 3 elements where this occurs in, right? So we could actually just say like, okay, well, let's just divide our array into chunks of 3. So like here's chunk of 3, chunk of 3, chunk of 3. And now we know that like we don't have to check every single element in here. So what we could do instead is we're just going to do this. We're going to say, okay, well, just every 3 elements, we'll put a little x. So x here, and x here. And now if something appears 3 times, it has to hit one of our x's, right? So we're going to put an x every whatever number of elements we need to occur. And now if something appears 3 times, it has to hit one of our x's, right? There's no way you can write 666, 3 6's without hitting one of them. And now all we have to do is check 3 numbers, right? So we're going to check this number, and this number. And this might, I think this will always be 3, but I think it'll always be 3 x's that we make total. So not necessarily like the length will be 3, but you'll always have 3 x's that you place. And then you just place the x's depending on how long your thing needs to be. So if this was like 1,000, and then each you need an element to occur like 300 times, you would place the first x after the first like 300, then the second x after the next 300, and so on, and the last one's at the close to the end. So then we just need to know for these 3 elements, like a 6 has to be in here, right? Like if we go back to this array and we actually put in these numbers, 6, 6, 6, 6, 7. I think we screwed this up a little. Oh yeah, there was a 2 over here. So It was like this, 6, 6, 6, 6, 7, 10. There we go. Let's get rid of this. So essentially we know by placing our x's strategically where there is only a gap, right, of like whatever we need here minus 1, our element's going to hit one of these x's. So now that we know we can check like only a few numbers, and one of these numbers has to be our answer. Now what are we actually checking for? Well, let's go back. So our array is sorted. So the elements we're going to be checking is we're going to be checking this 2, we're going to be checking this 6, and then in this case we're going to be checking this 10. And so what we can do here is, because it's already sorted, we can just perform a binary search. We're only going to have to perform a binary search for a few numbers, and we can get two things. We can get the leftmost index and the rightmost index in the array. And that's basically all we have to do for the problem. So to get the leftmost index is pretty easy. You just, let's walk through that actually. So let's get rid of some of these x's and just show that part now that we know that like our number has to be in one of these x's. So let's say we are searching for this 2, right? So what we're going to do is we're going to have 2 pointers for a binary search. You could optimize this a little bit to start at like better locations, but it's not really going to matter. Like it might make it a little faster on LeetCode where like if you checked this section before, you can now start checking at this section, but it doesn't really matter. You can just search through your whole array to make the code easier. So yeah, so essentially if we're looking for the leftmost and rightmost index of 2, we need to do 2 binary searches. So first, we are going to do a left binary search to get the leftmost. So the way that's going to work is pretty straightforward. We're just going to get some pivot points. So in this case, it would be like over here. So let's say the pivot point is over here. We're just going to check like, is this number equal to the number we're looking for, or is it bigger or smaller and so on, right? So this number is bigger, so we need to go left. So what's going to happen here is we're going to move our pointer over here. We were over here, so now we need to go over here. Now this is our binary search. Then we're going to get a new pivot point, which is going to be like over here. And this number is what we're looking for. So we're going to record this index. We'll just record like index 1. And now that we found it, if we're looking for the leftmost index, we are going to actually see if there's anything to the left of that. So we're going to go over here. We're going to check, is there anything to the left of that? No. So if this is too small, then we're going to try to go right, and then we'll be out of bounds. So we get the leftmost index of 2, which is at index 1. Then we do this again to get the rightmost index. So it's the same. It's going to be the same kind of thing. So we start with a pivot over here. This is too big. So we will move our our right side of the binary search over here, kind of like the first step. Now there's going to be a slight difference here. So now we're going to find this again, right? We're going to find this again. So we're going to say, okay, this might be the rightmost index, who knows? So we're going to record that. So this is index 1, and this was the leftmost index. And now the difference is before we were looking for the leftmost, so when we found a match, we go left. Now when we find a match, we go right, because we might have something to the right that's better. So instead of going left, now we go over here. Then we get a new pivot again, which is going to be this pivot over here, and we find this value again, which is at a better location. So we replace our old number with this one, and then we go right again. And when we go right, this is too big, so then we'll try to go left, and then we'll be out of bounds, right? Because what's going to happen is one of these, like the left is going to be, or the right's going to be bigger than the left. So we get our 2 indexes for 2. Then we simply check how long. If we have the left and the rightmost index, which is these 2, then we can simply check, okay, well, how long is that distance? So that's just the standard right minus left plus 1. So this is 2 minus 1 plus 1, and we get 2 here, right? So we get 2, but what do we need? We calculated we need 3, right? We calculated this, so this number doesn't work. So then what's going to happen here? Oh, that is, okay. So then what's going to happen here is we're going to do the same thing for the next number we're checking. And remember, we're checking every 3 in this case. So we check this 2, then we check this 6, and we're going to get the left and the rightmost index. Same kind of thing with a binary search. I'm not going to draw out the pointers. You do a left search to get this index, right search to get this index. Now we'll have a 3 and a 6. Then same thing, we check what's the width of this whole thing. So it's 6 minus 3 plus 1 equals 4. And now that means that 6 occurs 4 times, which is greater than 3. So we found our answer. And that's basically it. Once you realize that, like, okay, I need my thing to occur 3 times, so I can just put an X at every third number. And the beauty of this is you're only going to, like I said, you're only going to have like 3 X's. So the whole time complexity of this is going to be like you're going to have like 3 x's, and for each x is you're gonna do 2 binary searches. So it'll be like 3 times 2, and then each binary search is log n. So this is like 6 log n, which is log n. So now we were able to find our biggest element in log n time as opposed to linear search. So I thought this was kind of cool to share. A little bit trickier. Definitely not too bad. Like this turns it probably into like a medium problem, I think. Because like there's literally a medium problem that's like find the left and right index of a number in a binary search. So we're just going to write a generic binary search with a few like, with a variable saying if it's left then it's right, and then we'll just change it based on that. And yeah, so now we can code this up. So we're going to calculate, first of all, our needed number. And that's just going to be, like I said, the length of array mod 4, or 4 divided by 4 plus 1. That's how many we need. Then we're going to make a generic binary search function that's going to handle both left and right binary search. There is also bisect left and bisect right in binary search in Python if you want to use those, but I usually don't use the built-in stuff, so I'll just make one myself. So we're going to look for a target, and we're going to check is it a find left or not. So it's going to be true if we're finding the left side and false if we're finding the right side. So we're just gonna, like I said, you can make these left and right a little bit better, but too lazy for that, and it's honestly not going to speed it up that much more. So we're just going to search through the whole array, and we're going to initialize our result variable based on if we have the left. So if we have the left index, if we're trying to find the leftmost index, we'll just initialize our result to be infinity because we're trying to minimize, and otherwise, so we'll say like this, if find left is true. Otherwise, let's make it negative infinity, because if we're trying to either minimize if we're going left or maximize if we're going right. So there's like 2 lines of code difference in the binary search for left or right. So I'm just going to use this find left variable to handle that. And we have this part, while left is less than r or less than or equal to r, standard binary search. So you just do this to get the pivot. Now we have 3 cases, right? So if the number at the pivot equals the current number we're looking for, now it's going to depend where we're going. So we're always going to record, but now to move, we're going to figure out where to go. So if we're trying to find the leftmost value, if this is equal, we're still going to go left. So if find left, then we're going to go left by doing this. And if it's equal and we're trying to find the rightmost value, we're going to go right. So we will go over here to this is to go right. And the rest of the code is basically the same, I believe. Yeah, so if, then we have 2 other conditions, I guess. So we have an else if, or elif, array p is greater than the target. So if we're at an index that's too big, we always have to go left. And then the last case is if we're smaller than the target, we always have to go right. So that doesn't matter which one you're searching for. Yeah. And finally, we can just return the result. So now what we have to do is we just have to index through all of the available indices that we have to check. So let's say needed is like 3 in this case. If the first index we need to check is 3, then what we need to do is we need to start at index 2, right? So for example, let me go back to the picture. So let's say we need a length of 3. The first x we have to check is at index 2, right? It's whatever the number is minus 1. And then we just keep increasing by the amount we need. So if it's 3, then we just like start here, and then we do the next one 3 over, and then the next one 3 over, and so on. And like I said, you're only going to have to increase it a few times because this needed is reliant on length of the array over 4. So it's going to be like a fourth of the array, or a little bit over a fourth of the array. So you'll only have 3 of them to check. So yeah, so what we're going to do here is we're going to say for I in range, the first index we're going to start at is, like I said, going to be at needed minus 1 because it's 0 indexed. We're going to go all the way up to the length of the array until we get out of bounds, and we're going to increase it every time by needed, right? So if it's like length 3, we'll check index 2, then index 5, index 8, and so on. And one of these has to have our number because our number can't avoid all of these x's because these x's are needed minus 1 apart. So if the x's are 2 apart and the thing has to be 3 or more, then it can't avoid all of them. Okay, so now we're just going to get the number at the x. So current equals array I. And then we just get the left bind and the left side and the right side. So we can say like left equals binary search The target is cur, and we are checking for the left, so we'll pass in a true value, and right equals binary search. Same value, but now we are checking for the right, so we'll pass in false for the left. Now we simply have to check the length of this, so if array minus left plus 1 is greater than or equal to needed, then we found the length we need, so we can just return cur. And we can technically return like -1 or something at the end, but this should never hit because they're just guaranteed to be a result. So we can throw it in there, but it shouldn't really matter. All right, let's take a look. And there we go. And this is all over the place as usual. So, you know, if you just run it a few times, then you get a good result. Yeah, so like I said, we can go through this time complexity here. So for every single index that we check, we do 2 binary searches, which are both just log n. And we are only checking 3 indices max. So this is just going to be like 3 log n, which is log n. And yeah, for the space, we don't have any space. We just have like a few variables. So, and yeah, I did think it would be interesting to do this as opposed to the general, just like count up the number, because count up the number is like a super easy problem. So there's like kind of almost no point in doing video for this one, but this one's kind of cool. So yeah, hopefully this was helpful, and definitely something that you can use in the future. There is also another thing that you can use if it appears more than half. Instead of binary searching, you can just like have a count. I think it's called like the Moyer-Born voting algorithm or something, but you can't do this if it's more than a quarter. So just figure out, this is at least a little bit common, figure out like, okay, if I have to have a consecutive sequence of this many numbers, where does it have to lie, and how can I structure my searches to make sure that I always hit the number? And yeah, that's going to be all for this one. So hopefully you liked it. If you did, please like the video and subscribe to the channel. I'll see you in the next one. Thanks for watching.